Right, so now we're going to talk about the Poisson equation. So this is a little bit like the Dirichlet problem, but except that now the differential equation itself is inhomogeneous. So let's consider an equation of the form. Right, so nabla squared w is equal to f, and w is equal to g on the boundary. So previously we had talked about the Dirichlet problem where this f was identically 0. And what we're going to see is that one way to approach the Poisson equation is to break it up into two parts. Okay, so one way to approach this right is to break it into two parts, two simpler problems, one of which we've already looked at. Okay, so let's look at the plot where nabla squared acting on v is equal to 0, right? This is the Dirichlet problem which we looked at before. And then another part is where the the right-hand side, it's like to the differential equation is non-trivial, but where the boundary condition is trivial. Okay. And sort of it's easy to observe that if you take the combination of u and v, it's like you have a solution to the original equation, right? So you can observe that okay. Right. Yeah. So if you can solve these two simpler problems, then you found a way to solve the Poisson equation. So let me just sort of write these down. Okay. Okay. All right. So we've already discussed how to address this Dirichlet case. All right. So let's consider this other case where you have a non-trivial right-hand side here, but with 0 boundary conditions. So so the two simpler problems have the advantage, as we saw, that you can construct your the basis functions you've chosen. It's like to expand the candidate solution in so as to satisfy one or the other conditions, right? So when we talked about the Dirichlet case, if you recall, we considered basis functions which were harmonic, so they automatically satisfied the differential equation, and then all that was left was to find some appropriate combination of those harmonic functions so that they satisfy the boundary conditions. So as you might expect, it's like with this other case, right, you might want to choose basis functions which automatically satisfy the boundary conditions, and then only sort of picked the appropriate linear combination of those basis functions so that it satisfies this inhomogeneous part here. Okay, so have the advantage that one could choose the basis functions so that one of the constraints so here by constraints I mean either the differential equation or the boundary condition right is automatically satisfied. Okay, and then all you have to do is to pick the appropriate linear combination of those basis functions so that the other thing holds. Okay. We can pick sort of UIs so that they automatically satisfy the boundary conditions. And then sort of consider a linear combination U is equal to the sum over J of Cj Uj to try to make the condition that U squared, Nabla squared U is equal to F true or approximately true, right, in some precise sense. Okay, so this leads to the condition that Nabla squared sum over J of Cj Uj is equal to F, which we want to find an approximation of, right? Okay. All right. So that's sort of one way to look at this Poisson equation, right? Where you have non-trivial source terms, it's like in the differential equation, as well as a non-trivial boundary condition. And you can break it up into two pieces, one of which has a trivial source term, the other one which has a trivial boundary condition. And it's sort of easy to see that because of linearity, you know, the combination of the V and U's, it's like which are the solutions of these two different simpler subproblems, gives you something which then satisfies the original Poisson equation, right? Which is what we'd like to do. Okay, so let me just stop here for now, and then we'll talk about some approaches to solving this equation more generally.